My name is Sawyer West, and today I will be talking about how to model the zombie apocalypse. When a susceptible individual is infected with the contagion, they turn into a reanimated corpse, called a zombie, which attempts to infect susceptible individuals by transfer of bodily fluids. Zombies can be terminated by physical trauma to the head. With these assumptions, we can formulate a simple model with three populations: the susceptible, the zombies, and the removed. We will call this the SZR model. We can improve upon our model with additional assumptions. Some people may find shelter to lower the risk of contracting the contagion. Those who find shelter remain in their shelter for protection against zombies. A few lucky individuals may find that those they share shelter with have vaccine stockpiles. Less fortunate individuals who have been infected may not immediately zombify, forming an exposed population. Any individual that is killed and not in a reanimated state is part of the killed population. These additional assumptions add three populations to the SZR model to form the Schiesker model. Those who have been zombified will want to convert the susceptible and sheltering populations. In turn, survivor populations will want to reduce the number of zombies. We can adapt existing models of combat between opposing armies to model these casualties and conversions. The aimed fire model uses constants to describe the relative efficiency of the troops in the opposing armies, lowercase x and y, and scales the efficiency coefficients by the quantity of soldiers, uppercase x and y. We will continue to use the upper-lowercase representation of combat efficiency and number of soldiers for additional armies. We can expand upon the conditions at which individuals engage zombies in conflict. In a skirmish, surprise is not a major factor, and thus we assume the fighting efficiency of both the armies remains constant. In an ambush, which would typically be instigated by groups of survivors, the ambusher would have a higher combat efficiency, and the ambushee would have a lower combat efficiency near the beginning of combat. As time progresses, the buffs and debuffs to combat efficiencies degrade to approximate a skirmish. In a siege, the defender has some defensive advantage over the attacker, which does not dissipate as the battle progresses. However, if the defender does not have a secure supply line, then a siege becomes a battle of attrition. For now, we will assume that supply lines and stockpiles remain secure. Thus, defenders will have a constant buff to their efficiency given their defenses. While the aimed fire model holds when troops from Army X cannot be converted to Army Y, a slight modification is needed when describing susceptible individuals combating zombies. Namely, the rate at which the susceptible population is killed is the rate at which new zombies are produced. If there are no susceptible individuals to convert into zombies, then this term should be 0. Hence we use a step function, d of p, which when p is positive equals 1, and when not positive equals 0. Sheltered individuals are modeled in the same way as susceptible individuals, but with the advantage of buffs and debuffs. Finally, we want to consider individuals who are immune to the virus that combat zombies. The population does not contribute to the growth of the zombies upon death. However, zombies should be unaware of who is immune and who is not, and thus the zombies will still attack these individuals. The standard aim-fire model models these interactions well. Since zombies are walking corpses, we do need to take into consideration the rate of decay of the zombies. After some time T0 has passed from a zombie's creation, the zombie automatically is moved to the killed population, as they do not have enough chemical potential energy to function, or do not have sufficient musculoskeletal structure to move. As zombies decay, their combat efficiency should decrease over time. We expect a slightly decayed zombie to have little difference in combat efficiency compared to a fresh zombie, and a very decayed zombie not to have much less combat efficiency at a later date. However, we do expect a fresh zombie to have a much greater combat efficiency than a very decayed zombie. Thus, we will describe this modifier with a logistic-like curve with the top equation. It is important to note that this debuff does not apply to the zombie population as a whole. It applies to each zombie individually. Thus, the equation at the bottom of the screen represents the rate at which the zombie population decays. We also want to consider weather conditions that affect zombies. There are three types of weather when considering the decay rate of zombies: normal decay, slow decay, and fast decay weather. If there is clear weather, we assume that the rate of decay of zombies does not change. Examples of fast decay weather include when zombies are wet after rainfall and decay faster from bacteria, or when they are buffeted by sandstorms. Slow decay weather, like snow, chills the zombies and allows the zombies to last longer. We can represent the effect of decay by a weather decay constant, W sub d, which scales the effective passage of time on the zombies from creation. We will assume that both armies are always subject to the same weather conditions. When considering the effect of weather on the combat efficiency, it is fairly obvious that zombies do not have the intellect to prepare for weather. Thus, the relative debuff zombies have when confronted with harsh weather conditions is larger than when humans encounter harsh weather conditions. We also must note that the survivor population can reproduce. This applies positive pressure to the size of the population. We will assume those who are immune to the virus can reproduce with those who are not immune, and those who are sheltered can reproduce with the susceptible population too. We will assume any population growth from offspring will only contribute to the susceptible population. As in all population models, it is important to include an environmental carrying capacity. We also want to consider the rate at which individuals can find shelter, H, in which the shelter can become vaccinated, V. We will assume that individuals do not compete for shelter and that they find shelter at some rate. To the contrary, we will assume that there is only a constant amount of sheltered survivors which can receive vaccines per unit time. If we exclude predation from zombies, we have the population model to the right. When researching the topic of modeling zombie apocalypses, I stumbled upon an interactive simulation called Whiteset, where parameters can be adjusted. Many of the aforementioned models I discussed are included in this model. I encourage viewers to check out this site after the video. I want to leave the audience with some questions in regards to these models. How would you adjust the models to reflect the following? Disruption in supply chains during a siege, temporary combat efficiency buffs in an ambush, exposed populations' effect on models, moving very decayed zombies to the killed population, competition for shelter among survivors, the construction of new shelters, a more representative function for the rate of production of vaccines, time to produce a vaccination, administration rate of vaccinations, modeling the morale of the survivors and its effect on the rate of change of the populations, innovation of survivors over time affecting combat efficiencies, total collapse of military, healthcare systems, and governments, and offspring inheriting immunity. Thank you for watching. I hope you enjoyed.